So let's finish off our look at the Mosfet devices by working through this simulation here. Now if you go to the resources section, you'll see that there's a link, and if you double click that link it should open up this file here. So this is in the graphical calculator, which is freely available online, called Desmos, that's DESMOS. But if you just double click on the link it should open this up. Now we've got various folders here. There's only certain ones that we're interested in. We're not interested in the two at the bottom there. This is really just for me to actually build the simulation. Now what we have here is a Mosfet. So we've got the gate here, and you can see that the length of the channel is here and the width of the channel is here. Now the gate material here is just a metal. So we've got the metal top here. We've got the oxide layer down below it, and then we've got the bulk substrate of the semiconductor. So this is our metal oxide semiconductor, so that's our Mosfet transistor. In this instance here we've got the Nmos type device, so it's an N and an N in the channel here. And you can see here as well we've got the dotted line. So this dotted line shows us the area in which we have inversion. So in effect in this instance here, what's above this dotted line here is actually going to be an N type. So in this case here we're going to have a flow of electrons along the N type from this region all the way across inversion and out via the drain. So we've got the source, the gate and the drain, and you can see that we've got a P-type substrate. Now in the right hand side here we've got the transfer characteristics of this device. So we've got the voltage between the drain and the source, so that's the drain to source voltage, and we've got the current between the drain and the source as well up here, and you can see that we've actually got a transfer characteristic drawn out here. So we'll talk about that as we work our way through it. So let's first of all look at how we're going to use this. If we start off with the device type, you can click on this here and you can see that you've got an option. So there's 4 different devices we're going to look at. We've got the Enhancement Nmos, we've got a Depletion Nmos, we've got an Enhancement Pmos, and we've got a Depletion Pmos. Now these are defined by the threshold voltages, and you can see here that if we choose the threshold voltage to be +1, then we're going to be working with an Nmos device, that's an Enhancement Nmos device. If the threshold voltage is -4, then we're going to have a Depletion Nmos, and if we have a threshold voltage of -1, it's a Enhancement Pmos, and a threshold voltage of +4 is a Depletion Pmos. So we can choose these devices simply by changing the slider here. So for example now we've got an Nmos, Enhancement Nmos at the moment. You can see it's got an N and an N. Now I could change that to an Enhancement Pmos by making the threshold voltage -1. So if I put on -1 here, you'll see now we've got a P-type and a P-type, and we've got an N-type substrate. And you can see that this line here is moved, so it's just moving about in a random position at the moment because we haven't set it up properly. So let's go ahead, and we're going to in this video look at the Enhancement Nmos. So this is the one that we've really been dealing with through the start of the course, and we've been using this as our example device. So we'll go and choose that now. So we make that +1. So that's +1 volts. We know we're dealing with the Nmos device, so we can close this down. Well, 1 volt. Okay, so we don't need to look at that anymore. Just close that down. Now, the second option here is the actual beta values. So remember, we've got an option here. We've got our beta value for our Nmos, and we've got a beta value for a Pmos. So obviously we've picked the Nmos device, so this is the actual beta value that we're going to be using. So it's going to be this μnc tox width up and length. So I've already picked values for μn and c tox. So we don't need to bother talking about those. I could have picked kind of random values, but I've picked sort of typical values. Well, typical maybe a few years back, but they'll work for us just now anyway, and they'll give us the results that we require. Now the width up and length is the ones that we're interested in, because as designers we've got control over the width and length, so I can change the width and length here. Okay, now when I actually change the width and length, it doesn't actually change it in the simulation here. It doesn't make it longer or wider, the graphical, in a graphical sense. But we don't need that. We just need to be able to set the width and length values. And you can already see what happens here whenever I change the width and length. You can see that the graph actually changes, which is what we would expect. But we can talk through that just in a minute. So once we've chosen the width and the length, we're no longer interested in that section. We can close that down. So we know now that we're going to be dealing with the current equations for an Nmos. So first of all, we can get into the gate, source and drain. So this is where we pick our gate, source and drain voltages. So there we have it there. So we've got our gate voltage. So let's say we set off the gate voltage sitting at 5 volts and the source is sitting at 0 volts. Now we know, and obviously I've picked the drain, so let's say the drain is 4 volts here. So we know that this is actually the drain voltage and this is the source voltage, because in an Nmos device, the charge carriers are electrons. Electrons flow from a low voltage to a high voltage. So the low voltage is going to be the source and the high voltage is going to be the drain. So we get a 0 and a 4, so that's the source and the drain. And you can see here we've got the source and the drain here. So the source is going to be the low voltage, so that's the 0 volts, and the drain here is going to be this side here, which is the 5 volts. And you can see the gate here as well, it's going to be sitting at a value of 5 volts. And we can work out the VGS minus VT in this instance, which is a value of 4, and we've got our VDS, which is also a value of 4. So once we've set those up, we can get in and we can have a look at the actual current equations. So if you head into the current equations here, I'll open this out a little bit. So you can see here that we've got our linear equation, which occurs when our VGS minus VT is greater than or equal to VDS, and that's our current equation here, and it actually shows you the current here. So you can see that these two are undefined, but there's actually a current here. So this is actually sitting in a linear region at the moment, this device. Now the next one down is the saturation current when it's less than or equal to VDS, and you can see at the moment it's undefined because it's not in saturation. And the cut-off current is this current here, and again there's no cut-off current because it's not in cut-off at the moment. So we can see here that if it's in the linear region, we've got our VGS minus VT is greater than or equal to VDS. So you can see that we've got that here because we've got our VGS, so our VGS minus VT is 4 volts, and you can see here it's actually in this case it's equal to that VDS. Okay, so we're sitting just in the cusp between the linear and the saturation, and you can see that up here actually we're actually sitting right at this corner point here. So if I was to adjust the drain voltage, you'll see that we're going to be able to move up and down that curve, and you can see it's moving up and down the curve here. And obviously the main thing about this here is that not only are you see the actual current changing along the curve here, you can see the actual inversion layer depth changing as well as I change that drain voltage, and you can see that changing here. So we will talk through this in a little bit more detail just in a minute. I just wanted to show you the simulation and tool and how it works. So we've got access to these current values here. Now we've also got access to the current values for a PMOS device, but those are going to be undefined at the moment because we're not dealing with a PMOS device. This will only become active whenever we change the VT values, that is, we change the actual device type here, then those equations will become active and we'll be able to look at the PMOS device. Now there's nothing in these two sections here that we're really interested in. I've just used these sections in order to build up the structure of the device, but you're free to go and have a look at that and see exactly how I did it. And I've also got the curves as well, so I've built up the actual curves here, which is the transfer characteristics of this device in this section, and again you're free to have a look at that and see exactly how I've done it. Now if you're interested in, you want to understand how I've built up the actual device up in these two sections, then feel free to get in contact and I'll talk over exactly how this is working. So as I said in this video here, we've had an introduction to this simulation, but what we're going to do now is we'll talk through an actual device. So we're going to talk through the Enhancement Nmos in this video. So let's go ahead and we'll do that now. So let's have a look at our first device, which is going to be our Enhancement Nmos. So if we set the threshold voltage at 1 volt, then we know we're dealing with an Enhancement Nmos device. So I've already done that here. Now let's see what happens when we adjust the width and length. So at the moment the width is set at 10 and the length is set at 2, and what we're interested in is how the current changes through this device. So if I was to make the width a lot larger, is the current going to go up or is it going to go down? Well, the common sense way of looking at this is the width here, and it's the same as a river. If you've got a wide river, then you're going to get a larger volume of water flowing through than if you had a narrow river. So if I was to increase this value here for the width, you'll see that the amount of current that will flow from the drain to the source is going to go up. So you can see here that the whole curve moves up the way. So it means we're going to have a greater current flowing through this device if the width of the device is greater. Now what happens with the length of the device? Well, there's the length of the channel here. Now if we were to make the channel a lot longer, then we're going to have less current flowing through the device. If we make the channel a lot narrower, then we're going to have more current flowing through the device. And you can see this here. If we were to make the channel smaller, so the channel length is 1, you'll see that the current value increases. And you can see it decreases here as we make this value larger. So that's hardly surprising. We know that the current here is given by our width upon length ratio here. So that's reasonably intuitively obvious, so we can move on and we'll look at the gate, source and drain voltages. Now I've already set this one up with the gate sitting at 5 volts, and I've deliberately set the drain and the source voltage at 1 volt each. Now you'll notice that there's no side here that says source or drain, because in this instance here, if the source voltage is the same as the drain voltage, we don't know which side the drain or the source is, because we've already defined the source as the place where the electrons come from. Electrons come from the low voltage side and they travel to a high voltage side. But the low voltage side, which would have normally been the source, is actually sitting at the same voltage as a high voltage side. So really what we're saying here is that even though this device here, it may be sitting in the linear region or it may be sitting in a saturation region, it doesn't matter, that the actual current flow is going to be 0. So if we're sitting here and we've got an inversion layer all the way down to this point here, then the device in effect is going to be in a linear region because the inversion layer exists all the way along the channel, but there's not going to be any current flowing. And you can see here we've actually got this in the simulation. It's in a linear region, but the current flow is going to be 0 amps. Now here's an interesting thing here. What happens if we were to change the drain voltage? So in order for the drain to be defined as the drain voltage, it's going to have to be higher than the source voltage. So what we could do is we could pop the drain voltage up. Now you can see as I lift that drain voltage, we're heading up along the curve here. So you can see that the current here is changing. It's getting higher and higher. It's a larger drain source current. Now it's quite reasonable for you to look at that, and if you notice here that the actual depth of the inversion layer here at the drain side is actually decreasing. So you might be saying something along the lines of, well, I thought that if the inversion layer was larger, then we're going to have a larger volume of, in effect, current flowing through the device, then therefore the device current IDS would go up. If this thing here, this side here, was to become thicker, that is, the inversion layer was to become thicker, but that's not actually what's happening here. You can see it's the opposite that's happening here. But actually, as we make that inversion layer wider, then the current is actually going down, and as we make the inversion layer there narrower, the current is going up. Now, the reason why this is happening is that the current is actually a rate of change of charge with respect to time. So this is just like a pipe with water in it. So if we have a wide pipe at this side here, then we've got a large access to water. But as the pipe narrows, the amount of water flowing through here, the actual, we've got a backup of water here, we've got a high pressure water at this point here. So the rate at which the water passes this point here is very large compared to this here. And what we're actually interested in the current is actually the rate of the charge. Okay, so it's the rate at which the charge passes this point. So the greater the rate of the charge passing that point, then the greater the current. Okay, so that's why when the channel here narrows, the current actually goes up. So you can see that that's modelled here, and we can see that when we get to this point, exactly on the point here, we're sitting right at the cusp here. So at this point here, we've got our VGS, our VDS is equal to VGS minus VT, right at this point here. So we're sitting in the in-between point, just between the linear region and the saturation region. So now if we were to increase that drain voltage even more, you'll see here that we're now in the saturation region and we're running along this part of the curve here. And you can see we've got a pinch-off point at this point here. Now, the saturation current just remains the same in this model. Now, in an actual transistor, it would actually change. It would go up a little bit like this. But we're not bothered about that second order effect here. We want to just keep it simple. So as we increase that drain voltage, you'll see that the saturation current just remains the same. So the channel doesn't exist all the way along, but the electrons have got enough energy once they get in here to jump over onto the drain side here. So this models our Nmos device. Now, a thing to note here as well is that if I was to come down here and I was to make the drain voltage now say less than the source voltage, then you'll notice that the source and the drain terminals here are going to flip. So what you see this happening now. So if I was to make this drop down below 1 volt, and you'll see that we've now got the drain at this side and the source at this side. And you can see here that although it's not modelled here completely, we've got the current now flowing not in this direction, but the current has changed and it's flowing in the opposite direction. So the electron flow was originally from here to here. Now the electron flow is going to be from the low voltage side to the high voltage side. So the low voltage side here is actually now going to be this side here, and the high voltage is going to be this side here. So it's actually swapped round about just because we've changed in effect the terminals here for the drain and the source. So what we would get is we would get the same characteristic here, but it would come down like this, and then it would come like this. Okay, so I haven't actually modelled this side. I've only modelled one side of it, but we only need to understand the current flow in one direction. So in effect, the current can flow in both directions here, and the drain and the source can actually change. But we'll put it back to the way that we're actually going to be using this device, and we're going to use the device in the region, this region here. Now we're actually interested in using this device here as a switch. So what we want to know is when is the device on and when is it off. So we can see that the device is going to be on whenever the gate voltage is high. So let's say 0 is a low voltage and 5 is a high voltage. So then our gate at 5 voltage will ensure that the device is on. So the drain then would have to be a greater value than the source. So let's just, for example, put the source at 0 volts. So we've got our gate at 5 volts, our source at 0 volts. Now the drain is any voltage above the value of 0 volts. So let's just put the drain a random voltage, say 3 volts. So what we can do here is that if we were to change the gate voltage, let's see what happens to the inversion layer. You can see that this entire curve entire line starts to move up the way. So the inversion layer here becomes smaller and smaller. So let's just continue that down and see what happens. Now we know that the threshold voltage is 1 volt. So as soon as we get down to the gate voltage getting to 1 volt, at that point there, you can see here that we have got no inversion layer across the entire channel. So it means that at that point there, the device is cut off. So there's no current will flow through that device, because now we've got an N and we've got our P-type region, and we've got an N in our P-type region. So we've got back-to-back PN junctions here, so no current will flow down along here. And you can see here in the simulation we've got it's cut off there, and there's 0 amps flowing through this device. So again, we could turn the device back on by ensuring that the gate source voltage is greater than 1 volt, and just at this point here, that's the device turned back on. Okay, so we can adjust the current through the device by adjusting the width and length of the device, and we can adjust the current through the device as well by adjusting this drain voltage. Okay, so this is us adjusting the actual point at which the device is in operation along the characteristic curve here. Now, what I suggest you do is you open up this simulation and you have a little play with it, and you adjust some of the values and ensure you understand exactly what's happening with this. We'll also use this simulation here in order to work through a few of the examples which are going to be in the quizzes. So let's move on and we'll look at the next device, which is going to be our Depletion Nmos.